All right, we've got 3 days left. We've got a nice ASCII art happening on the left here. We've got day 23, 24, and 25 left. So let's take a look at day 23. Looks like there's some magma, yada yada, something happened. Wait a second, is there an active volcano exploding and they're trying to plant plants? Here's our input. Let's get that in. So we're using test.txt from yesterday. I guess we can just use the same thing. We'll need a parser for that, so it'll be dots and hashes dependent on the position, so probably very similar to the iterator parsers we've been using. Hashes are elves and dots are empty ground, so probably an enum. We've got north, south, east, west, and diagonals. The elves follow a time-consuming process to figure out where they should go. Okay, speed up this process considerably. The process consists of some number of rounds during which elves alternate between considering where to move and actually moving. First half of each round, each elf considers the 8 positions adjacent to themselves. If no elves are in one of those 8 positions, the elf doesn't do anything. Otherwise, the elf looks in each of 4 directions in the following order and proposes moving 1 step in the first valid direction. So if there's no elf in the north, northeast, or northwest, then north, similar for the other 4. So after each elf has had a chance to propose a move, the second half of the round can begin. Simultaneously, every elf moves to the proposed destination if they were the only elf to propose moving to that position. If 2 or more elves propose moving to the same position, none of those elves move. Okay. Finally, at the end of the round, the first direction the elves considered is moved to the end of the list. Okay. As a smaller example, consider just these 5 elves and then whatever, end of the round. To make sure they're on the right track, the elves like to check after round 10 that they're making good progress. Count the number of empty ground tiles contained by the smallest rectangle that contains every elf. Okay, so find the elf in the, I guess, lowest position and highest position. In the above example, that rectangle is this. So it's, well, I can't really select it, but it gets rid of the leftmost, the rightmost, and the bottommost. So we have to find Y min, Y max, X min, and X max to draw this triangle or rectangle. So in this region, the number of empty ground tiles is 110. Simulate the process and find the smallest rectangle that contains the elves after 10 rounds. How many ground tiles does that rectangle contain? So it's 110 for test number 1. So we'll put that in here. And then when we think about the problem, we have to do things like iterate over every individual position, but also get the 8 positions around it every time. Normally, I would say that that's a case for ND array, which is a matrix crate, because we can run windows. So we could do a 3x3, but that would only take us from this position. So we can never get this position doing that. And we have to, because this elf is in the top position and it's considering moving somewhere, right? So I think we're best off storing this all as a B tree. Also, all of the empty space everywhere is infinite, right? So they can move in any direction. So we're not actually going to represent the empty spaces, I don't think. We can't hard code the checks for each direction because it will change each time. The rectangle here, to select that at the very end, having a matrix would be really useful because ND array would allow us to select a slice from some index to some index in a 2D way. So it would make the final comparison very simple, but we can also just write that iterator as well. It's not a huge deal. So I think we iterate through this, right, for the parser. We give the positions to each of the hashes, and then we basically iterate for each elf. We try to find each of the positions that we need to from the B tree. Then we construct a new B tree for the second round, and then we have a new B tree basically every single time. So we're not actually going to have an enum because we're only going to have elves. So we're only going to have positions, really. I guess we don't even need a B tree map either, right? We need a B tree set because in the end, if we, or a hash set is probably what we're going to use if I choose to use the IVEC2 for the value. So if we do like a hash set here, then we can do hash set.get on a particular index. If that index is in the hash set, then we have a position. If it's not, then we don't. So I think we're going to use a hash set here, which is interesting. We do need to bring both of these in. So glam and hash set. Of course, we aren't returning anything yet. So the return value is an error, a type error. So I think we'll take the terminated iterator approach again. So let it equals iterator, terminated line ending, alt car dot, car hash. And I've already written this wrong. Call expression requires function. I think this is a parentheses issue. Iterator terminated all, but do rip grep iterator A5, and I'm going to do it in the upper directory. Then we will get anything that matches iterator inside of my Advent of Code repo plus 5 lines after it. So this is day 23, the one we're working on, but it should also show up in other days. So for example, day 20. So input is the first argument, and we don't actually handle the error here. So it should look more like this. Do we have line ending? I'm also going to take this opportunity to grab this enumerate. We also have to call finish. I know there's another finish in here, so maybe I'll do that too while we're here. Finish, and I'll use C5 instead. So C5 for rip grep will do context around it. So if we do it.finish here, then it'll show a couple lines before and a couple lines after. So the result will be something like this, whereas the values we want will look something like this. And this is just code that we wrote in other days. So we've got an iterator parser from nom that takes the input that looks for either dot or hash. This needs to be many1 because we'll get a bunch of them. Terminated in line ending. So we get an iterator here. We should be able to do it.enumerate. Cannot borrow is mutable because I didn't declare the iterator as mutable. So if we iterator.enumerate, then we'll get each of the lines, which we need to map over. We'll get line in here. If we check the type, we get usize string slice. So this will be the y index and then the line. It's interesting to me that we're getting string slices here for line because I wasn't expecting that. So let's get this running to see the output. Map. So let input not underscore. Let underscore, I guess field is what I usually call this, equals map input unwrap. And then we want to debug the field. And that's not going to come through yet because it'll panic. 34 not yet implemented. So I'm not logging anything out. I feel like I wrote this wrong. Many1, either, I guess we can do one of here. We don't need to do alt. Alt is a choice. But it makes more sense to write this as dot hash. So we end up with line 31, but no debug. That feels wrong. Let's debug numbers. Numbers is the wrong variable name here, but yeah, numbers is an empty array. So what did we do here? Iterator input terminated. We passed the input in here. The input is test right now, right? So it's dot or hash. Did I write terminated wrong? I did. I wrote terminated wrong. Oh well. So it's terminated is the parser that we want, and then the line ending, which makes more sense. Like parse terminated, this thing terminated in that. So we have y in line, and line is no longer going to be a string slice. It's going to be a vec of cars here. So if we enumerate over the line and we filter map, we can match on C. C is going to be a reference to a car. So we'll either have dot, which will be none, or we'll have hash, which will be sum ivec2 new x, y. And it's telling me that ivec2 is wrong. I guess this needs to be flat map as well. ivec2 cannot convert a usize to an i32. That's why these need to be treated as i32s. Then we've got that ownership of y issue that we've hit in the past with specifically the pattern flat map, where we have a variable here and then we do line. So in this case, we can take let me just expand this so you can read the error message with me. This closure might outlive the borrowed value y. Y is borrowed here when we're doing the sum value here. Y is i32. And the closure is returned because we're returning the iterator. We're not returning a collected value, right? If we collected here, then that solves our issues, right? We have another issue, which is this C value, which if we have anything that isn't a dot or a hash, then we need to panic because we just parsed things that are dots or hashes. So this should never happen in our program, which is what panic is for. So we can do this collect if we want to. If we don't want to do the collect, we have some options. For example, we might have to move in this closure, but now we are borrowing line. So cannot return value referencing local variable line, which is defined in flat map as well. But we can take ownership of that data as well using into iter. So we can either take ownership of the data that we need and move the data that we're referencing in to this closure, or we could collect into a different container. Both options are valid. Whatever you want to do in your particular situation is totally fine. It's easier from a beginner's perspective to collect into a vec. You do not need to pass around iterators all over the place. And then we get basically a list of all these vecs, ivec2, 4, 0. The reason I used an ivec is because I want to be able to generate negative values. So when we go to look for all of the elves that are around or all the spaces that are around a given character, I want to be able to look for -1, 0 kind of values inside of the B tree set instead of having to actually check to see if we're going to go below 0. So let's finish up our parser here. And I'm going to rename this variable to elves because they're elf positions and it's supposed to be a hash set. So let's hash set from elves, which should be fine. From ivec2, of course, is not implemented for hash set. The other thing that we see here is from tn with the braces here. Of course, we don't need to do it down here in the first place. So when we do this vec, we could do a hash set. And we could collect into a hash set of ivec2s, which means that we will get the hash set in the elves variable right here, which will pass it back. So remember that collect is super powerful. If we're collecting into any container, like a vec or something like that, you can probably collect into the thing that you want. So definitely look at that before you go around like manually converting. So if we look at this and then what, I bring up the test input 6, 5, 0, 1, 2, 3, 4, 5, 6. So all the way over here, 0, 1, 2, 3, 4, 5 has an elf in it. 3, 5, 0, 1, 2, 3, 0, 1, 2, 3, 4, 5. There's an elf here as well. Looks fine to me, basically. So we have to code in all of the movements. It says you can speed this process up considerably, which I don't know what that means. If they really wanted me to know, maybe they should have told me. But we have an order here, right? So there's 4 steps. We check the top 3, the bottom 3, the west 3, and the east 3. And then each time we go through the entire cycle, we change the order here. So really, I feel like I want to write a function that operates on 3 elements and then pass around these indexes or the difference in indexes. So we can do something like let checks equals like a vec, and each of these are going to be 3. So it's going to be like ivec2 new, what is this? -1, right? We're going to do the north first. So -1, 1. We do this 3 times for 4 positions. So we've got ivec2 new this. So x values change. So north, this is south. So all of these are -1. Is this west or east? This is west and then east. So this is going to change for the y values are going to be negatives, 0s, and then 1s. And the x values are going to be negative for west and then positive for east, right? None of the commas exist here, but that gives us a 3-element list for each of the checks that we need to do. And we could probably do like a take 4 here. So if we do a cycle.iter.cycle, right, then every 4 that we get is going to be this batch. And every time we're done, we can do a .next so that the next time we do take 4, it iterates. Let's get rid of the random debug I have here. Okay, so we've got 2 halves of the move. We need to propose a move. If no other elves are in one of these positions, the elf does not do anything. Okay, so maybe we do nothing to start. The elf looks in each of the 4 directions in the following order and proposes moving 1 step in the first valid direction. So is the first valid direction just north, south, east, west, or is it diagonals? Yada, yada. The elves like to check after round 10. So we need to do 10 rounds. 4, 0.10. Then we do we'll call it local checks equals checks.take 4. Of course, that's not mutable, is it? Mute. And then what else do we have? Creates a temporary that is freed while still in use. Is that because we need these to exist if we're just going to iterate over them? So we could do this and then let mute checks iter equals checks dot this. And we do checks iter dot take. So if we clone the checks iterator, we can skip I and take 4, and that should give us the offset for every round. So if we do this, then we are given a little bit easier to see if we do this. So if we do this, we get each check as a group of 3. And I realized I'm not printing out anything for each round, so we have no idea when they start. So it's hard to show. Let's do this, print start, just to show in the output. We've got 1, 2, 3, 4, and then start. So this is -1s, and this starts with -1, 1, and then -1s are the second. So we are moving up 1 every time we do an iteration here, which is exactly what we want to do. Now we need to iterate over every elf, right? So for elf in field.iter, we need to calculate it for each elf and then do another check. So we're going to need to keep some state around locally. So what do we actually need to store? Because we're going to need to access this by, I think, the position that these elves want to move to, right? So our decision about whether they can move in the second phase is determined by if they were the only elf to propose moving to that position. If 2 or more elves propose moving to the same position, none of those elves move. So we could do this as a B tree map or a hash map where we do an entry call for the desired position. And if there's an entry that already exists, that means another elf tried to move there, and we can change it to be none. So the values will be something. We could store a custom enum here that would help us debug maybe, but none of the elves move if 2 or more are proposing to move to the same position. So we've got a set of elves that don't move, which that map doesn't give us, and then a set of elves that do move. So I think we store them as vecs. So I'll have a hash map from position to vec. And if it's a vec, then we just insert the value. If it's a single item vec, then we insert the key. So it's a hash map of ivec2 to vec ivec2, which we need to instantiate every round. We haven't brought this in, so I'll just do it like this. We'll call this proposed moves. So for elf in field.iter, we calculate an elf move. That elf move gets inserted into this hash map, so we end up with a key or a hash map of keys that are the positions elves want to move to and a set of values that represent the elves that want to move there. So I think for field, we do a mute field because we're going to need to change this all the time. And then for elf in field, or not for elf in field.iter, then we do proposed moves .iter .map. That flat map probably is the right move here. And then we get key and value. So this is elves to move, and this is desired position. If elves to move that length equals 1, then we return desired position only because that elf will have moved. Else we return elves to move. And I think that gives us a issue. If elves to move dot length equals 1, expected because of this. If and else have incompatible types, that's what I expected. Because every if expression for each of the return values that comes out of it needs to have the same type for those values. So in this case, we have a 1-element array, and in this case, we have elves to move, which is a reference to a vec. So we'll at least need to turn this into a vec. It doesn't really matter. We can consume this as well. So into iter, we're not going to use this as a reference itself. So flat map collect is going to collect into a hash set because we'll have flat mapped over it. It'll be a hash set of ivec2s because that's the value we'll need. And then we'll do field equals this. So that'll be the next field, and then we'll iterate again, which leaves us with the need to do the elf checks. So we need to iterate through each of the 4 checks. If one of those is valid, which means that the spaces are all empty, then that's the direction it wants to go in. So I think we do a find map, and this checks comes in as that ivec2 of 3 values. So these are the 3 positions that we need to check. So if we do checks.iter.all, we get a position here, right? So we get an ivec2, and we need to do field.get position is sum. So checks.iter.all positions, field.get position is sum. That returns us a Boolean, I think, which we can then sum checks1, which is the middle value. So it'll be, because we've set this up to be like the left, the middle, the right, or the bottom, the middle, the top, then checks1 is going to be the position that we want to move into. So possible move is an option ivec2. There's no guarantee that we have a valid move. I can't name this move, so I can name this move. Actually, let's finally do that. Why not? If sum our move equals possible move, I guess we can do let sum, right? Let sum equals this, panic. Well, actually not panic, because it doesn't matter to us in the end if there's a valid move here. So we don't need to return anything or whatnot. So we don't need let else. So we do if let sum whatever, then proposed moves dot entry with the potential move. So our move dot end modify. This will be value, and it'll be value dot push. So probably needs to be mutable. And we're going to push the elf. I think it's elf.1. right? I don't know why elf isn't coming up for the type inlays, but we want to basically, if we have a possible move, we want to take the, oh, also this isn't field.get is some, this is field.get position plus the elf. So field.iter is a hash map. So it should be position plus elf. And now we see what elf is. These are two references to IVEC2s. Cannot add a reference to an IVEC2 to an IVEC2. Do we need to really dereference both of these? That's awkward because then we just need to reference it again to do the get. But okay, whatever. That's fine. So what we need to do here is this position comes in as an offset. So we need to do the elf plus the offset when we do the field get, which means that when we do elf here, this is a dereference. Cannot borrow is mutable. So let's do mute possible moves. That's not the one that I wanted to make mutable. Let mute proposed moves. That's what we wanted, which we don't need mute on value then. So we do if let, we have a move. So if let sum possible move, which destructures the move out of it. We're using our hash to use the value move because we can't name this move because move is a keyword in Rust. For proposed moves, we do .entry for that IVEC. If it exists, we modify it. If not, then we insert a vec of elf, and then we do the thing that we did before. So we should, after all is said and done, have at least the field. I got rid of the to do, so it thinks that I need to return here. So we're panicking at 112, which is fine. Field is empty at the end, which doesn't feel right. If we debug field.length, we see that we get 2831. So I am not reinserting some of the elves that aren't moving because of this. Because if there's no possible move, we still need to do the same thing, just with the elf's current position. So proposed moves, instead of our move, is going to be elf, not end reference. That's not the key that I meant to hit. Dereferenced elf. So that should, yes. Okay. So we were losing some elves along the way. They were just trying to walk and plant seedlings and falling to the lava. So we've got a field here. We've got what I think is the positions of the finals. So this should be field.iter dot what? We need xmin, xmax, ymin, ymax, right? We need all of them. What is min set by? There's also min max, which are both from Itertools. Let's go find out what those are. First, let's find out what min max is. So return the minimum and maximum elements in the iterator. So we should be able to map over this and then just do x's is what this is telling me, which is nice. Min set is return all minimum elements of an iterator. I think that doesn't help us. So let's make use of min max, and it's min max by, which is very cool. So if we do field.iter min max by key v.x, then that works for this. And then we can do this again for y, min max IVEC2. So we do need to map over these anyway. Maybe we do the map in the iter so that we only get the x's and only the y's. So we'll just call min max here, and both of these will map v.x in that case, v.y in this case. We don't need to do the y there. Then we'll get min max I32s. I don't remember what the results are supposed to be. No elements, one element, min max. So if we do a let else here, we're going to match on min max y and min max x for the two values. These need to come from Itertools. So I'm going to copy that in using that little nice click handle and drop this right in the top and do use. Of course, I want to do this as a star because I want to use the shortened versions of the names. So we end up with a 6x5 rectangle. Is that for this the right size? That doesn't look right. 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5. That doesn't look right unless I'm using the wrong input. Did I use this one? Okay, so let's figure out what the issue is here. Let's print out, to start with, all of the values. 6050. Min max doesn't have a weird like condition where it only goes to 0, right? They're I32s. For each elf, we're doing a clone of the checks here. The checks for each of the 4, if we can find one where all of them is none. Is none is the right answer here. Dang. Although that doesn't change our answer, which is mildly hilarious. If checks iter all, field.get is none. So if they're all none, then we pass back the check. So let's let's bump this down to 2 iterations. Let's do field instead of the other thing. We could do a display implementation here to make this easier. The initial state looks like this, which is we are going to have to print this out because the indexes don't match up at all. So let's get print line with a debug or a display formatter field, right? Field, of course, does not have a display implementation at the moment. I'm going to bump this back up to 10 because it won't matter. Of course, doing field like this would require us to do a new type for the hash set, which right now I don't think I feel like doing. So let's do this instead. We're going to call print field with a reference to a field. Print field, of course, doesn't exist, so we can use a Rust analyzer to scaffold that out for us. It's not going to return anything. This is going to be a hash set of ivec2s, which I think matches for us. Looks good to me. Field is the hash set of ivec2s, so we should be good. And we need to do the same thing we did here with the min maxes, and then we do a little, 0 dot dot. We can't modify these actually, now that I'm thinking about it. I think we need to do x1 dot dot x dot dot equals x2, and then we Cartesian product it with y1 dot dot equals y2. We need to reverse these though, because we need y's to come first, simply because of how we're going to print this out. So we want y low to come first, and we want x low to come first. So we map, we get this position, match position, or not in position, we match nothing yet. We do yx here. We match field.get ivec2 xy. If it's some value, we don't care. It's just going to be a hash. If it's none, it's going to be dot. I think that we need to collect here into a string preferably. And then I'm going to do a print line exactly like we were going to do with output. And then this is going to be because these are U sizes because we did a range instead. So X, actually, are they going to be U sizes? What are they going to be? I think they're going to be references is going to be the issue. Expected a reference to an ivec2. Yeah, there we go. It's a reference to an ivec2. So we just destructure that when we do the get, or rather we create a reference to the ivec2 for the get, and then it prints out. And with any luck, we can join with a new line and it'll just work for us. Of course, it doesn't because we're doing every individual value. Chunks x2 minus x1, I think is the right chunks as U size, because that should be a positive number. And then I guess we just do the map here, or rather we can, intersperse? No, we'll do that map chunk dot. Oh, right, we need to into iter here for the chunks. The chunk, of course, is going to be a chunk. So we need to collect to a string, join with /n, print out, and we get these. We also probably want to print a heading, but we can do that round I, new line, and then the field. Of course, this isn't going to work because it's not a print line. Print line this, and then we also don't need the new line because we already have the print line there. So we're looking at something like this, round 0. We either need to do this at the beginning or the end. So maybe we do this, we do round or initial state here, right? And let's do a new line before. And then for here, for each of these, we'll do print line round I, but we're going to do I plus 1, right? Because the rounds have 1 index. So initial state, round 1, round 2, none of these are getting set is the issue. It's the same one every single time. So field, we are always getting back the same value. So it must mean that our checks are wrong. So let's do debug check. It sounds like the only thing that could be wrong here. So instead of checks, let's debug output. And then we need to return output too. That is a lot of output, but it seems like it's working. 0, 1. Oh, we don't want that though. We want this position, right? We want that. Okay, so now we're getting 10 for the spread and 12 for the spread. Bothers me a little bit that there's 3 random dots down here, but maybe it's just some overlapping stuff. Get rid of the output debug here. So we start like this, and then we get to whatever this is. This last one really makes me feel weird about it. So this is like a sideways T with a backwards L. That's wrong. The initial state output is wrong. So it must be the display. So if we Cartesian product y's x's map, and then we chunks x1 x2 minus x1 1 2 3 4 5 6, right? 1 2 3 4 5 6 7. So it has to be at least this for chunks. And now our output looks better, at least. So there's a sideways t, there's the backwards l, there's the right caret t, and 2 hashes. There's the right caret, there's the t, and there's the 2 hashes. Except that we don't get the bottom row either. Why don't we get the bottom row? It's y1 equals y2, x1 equals x2. Does this need to be... We're missing one of the bottom rows here, which means we're not printing it out. If I just tag a +1 on there, do we get the output? No, we don't. Am I missing elves from the original state? That is number one question. The field right here. I messed up. I did. I definitely messed up. I know where I messed up. I just figured it out. Where are we in that? There's a +1 in here that I don't need now for this. And then we want line ending. And this terminated. This trips me up every time, actually. It tripped me up the last time we did this too. We needed line ending or end of file because each of these lines can terminate in what it needs to. So this is 10. This is 9 now. This looks correct now. Is this in the right spot? That little hash right there? It is. Okay. So let's check the big one. This is 3 on off on. 3 on off on. Is it the before that? No. Nope. Those are wrong. So let's go back up and check round 1. Round 1. 4 empty spots. There's a backwards L at the top. That is not true. So we are doing our movement wrong, or at least our checks. So for each of the local checks, we need to check north, south, west, or east, right? We need to do a find map on the checks. So we're looking for either north, south, west, or east as a group to see if one of those is all empty. So the elf position plus the position that we want to try to move into needs to not exist in the field. I think that's correct, right? Because we do the checks first, consider the positions. If no elves are in one of those 8 positions, the elf does not do anything during this round. Otherwise, it's north, south, east, or west. It'll be the elf position plus checks 1, which is the middle check. That'll give us output, and this will give us the possible move by doing that find. So if we have a possible move, well, let's do it the other way around. This should have been a match. If we don't have a possible move, then we need to insert the elf by itself. The end modify here, I don't think ever can happen. So we would just insert the elf right where it is. If there is a possible move or a desired move, right, then we check to see if the move that we want to make exists in the proposed moves, and we modify that value if it does to add the elf. If it doesn't, we specify the single elf. Then we go over all of the proposed moves. So there's the desired position on the left and the amount of elves we need to move on the right. If the amount of elves to move is exactly 1, then that elf moves into the desired position. Otherwise, all of the elves that are there stay in their place. That sounds right to me. But it's producing the wrong behavior. So there's something I missed, or some logic error in the code. Should we try to do the smaller example first? This, of course, is only going to work for like 3 moves or something. So this is going to be our input. I'm going to ignore this test for a second, and I'm just going to grab that and stick it in here. This test is always going to fail as far as I know, because we don't actually have the answer to this question. But now we are doing the part 1 test works. So the initial state is 2, 2, 2, 2. That doesn't look right. 2, 2, 2, 2. Actually, it is right. Okay. So it's that top L space and then 2. Yep. 2 space right caret, 2 space right caret. Okay. So those moves are wrong right there. The top moves look fine, but the bottom moves look wrong. I wonder if we are properly iterating over the checks. So this checks, right? Let's make this only a single round. Let's do local checks. I thought I wrote this correctly the first time, but I am not sure about that now. So this is going to be a different kind of debug for us. So for check in local checks dot iter print line check check. This is going to be check in debug form. This is already an iterator, so we're just going to clone this so that we can iterate over it again. Okay, so this is -1, 1, which looks like the right one, 0, 1, 1, 1. Then the next one iterates next and goes south first, right? So those checks look fine. The proposed moves, I guess, is something that we could output. I still feel like it's a problem with the checks for each elf. So this is phase 1 right here. And then down here is phase 2. So let's debug proposed moves, I suppose. And for the small input, we end up with, it's unfortunate that we really don't have anything to compare this against. So 2, 3, 2, 2. The problem is these indexes mean nothing compared to the example. So 2, 3, right? There's one in 2, 2 right now. There's also one in 2, 4, 2, 1, 3, 1, 3, 4. So there's 2, 1, 2, 2. I want to say it's like this one, right? Or 3, 1, and 3, 4. 1, 2, 3, 4. 2, 1. Why is this 2, 2? Let's eliminate all of the elf non-moves. Doesn't make it better for us. So everything moves, right? So this one must move south. These two must move north. These two must move north. Except that this one and this one go to the same spot and don't move. Okay, so we're not capturing that though, for whatever reason. So the lowest elf, X0, 2, 0, 1, 0, right? Those are the bottom two. So it's got to be 1, 0. And what's the other one? 2, 5, 3, 5, 2, 3. Can 2, 3 and 1, 0 even reach? 2, 3 can go to 1, 2. So if 1, 0 wants to go north, it wants to go to 1, 1, right? If 2, 3 wants to go south, it's actually impossible for those two to hit. These are elves, right? Elves iterating over the field. Oh, this is... I was looking at the wrong field. Dang, hate when I do that. Okay, so we've got 2, 1, 3, 1, 2, 4, 2, 2, 3, 4, right? So Y value is 4, 2, 4, 1, 1. So this is our middle. 2, 2 is our middle. It wants to go to 2, 3. That's correct. Wait, no, that's wrong. It's supposed to go south. So why is it trying to go up? 2, 1 goes down and to the left? That doesn't sound right. Down and to the left is wrong. Is checks 1 what we really want here? Wait, why are all of these -1? Did I write this completely wrong? Let's see. So this is north, right? This is up 1. This is south. This is all down 1. This needs to be changing in X's. This is all west, and that's all north. Does that fix the output? No. So we've got this backwards L, and then the 2 at the bottom, and we've still got this backwards L, still got the 2 at the bottom, but these two haven't moved now. Those checks being wrong is not great. So 3, 0, and 3, 1, right? So 3, 1, 2, 1. This is 3, 1, and 2, 1. 2, 2 is mid, and we've got 3, 4, and 2, 4. So this is 2, 2, and this is 2, 2, 1? Why do we have 2, 1, and 2, 2? That must be these. I'm looking from the wrong direction. I'm going 0 at the top, down. Dang, that's what I need to be doing. Okay, I'm looking at the wrong values. Then I've written these checks incorrectly. If 0 is the top. If 0 is the top, then this is negative, and this is positive, and then these don't matter. Yes, there it is. 2, and then the arrow. That's what it was. I flipped my y-axis. So let's get this ignored. Let's get back on our regular test, and let's get this debug out because debug is pretty noisy. Okay, so now we have 1, 2, 3, 2, 4. 1, 2, 3, 2, 4. 3, 5, space 2. 3, 5, space 2. Okay, I'm inclined to say that this is correct now. Vertically, it's correct as far as I can tell. I'm going to assume that because we did round 1 correctly, that all of the other rounds are correctly implemented. That is, I'm going to get rid of the printouts for all of this because it doesn't really make sense for me. And we've got 8, -2, 8, 0. And we've already written what we need to do here, I think. So by definition, right, we only store elves. So if we do 10 times 8, right, we do this times that, what we end up with is the square size, right? 10 and 8. That doesn't sound big enough because we're going to have to subtract all of the, is this +1? Is that the issue? Am I not including one of these in that math? 11 and 9. then is still not enough. I think we need that at 110, don't we? So that rectangle is 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 7, 8, 9, 10, 11. It's 11 by 12. So let's get a print field in here. And let's get a look at, that's round 2. That's the problem right there. That's, I forgot to re-up us to the right amount here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 11 by 10, which is 110. What is the 1, 2, 2, 2, 3, 1? That's wrong. Did I need to do one more? End of round 5. 1 space 3 space. Nope. Are we even correct for round 2? 3, 2, 3. End of round 2 is not even this. What is going on here? End of round 1. 1, 2, 3. 1, 2, 3. 2, 4, 3. 2, 4, 3. 5, 2. 5, 2. So the end of round 1 is correct. The end of round 2 is 3, 2, 3, which is wrong. Okay, so we've got an issue here. This one is supposed to go up, right? Because if it's sitting here and it checks north and there's nothing there, it should go up. Whereas I think all the other ones do. Let's do this. Let's bump it back down to 3 because this output is so gigantic. I'm going to need to modify this output, actually. So we've got proposed moves from this, right? So whatever Y max is this one up here. So we've got 3, 5, 0, 4, 7. 7's our winner so far. I think 7's our winner. There's 2 at 7, so it's got to be 8. That is incorrect. What have I done? Let's do this. Proposed moves.iter.map key value. We'll do the values as a debugged output. So now we have a really bad choice of debug that I just proposed moves.iter.whatever. Let's make this a for each instead of a map. Okay, so now we have a better representation here that we can actually look at and scan in a single page. And round 1. So there's an initial and it moves to this. I think this one was correct. 1, 2, 3, right? 1 space of 3. Yes, round 1 looks correct, at least in the part that we care about, the top part here. Round 2 is 1 and then a space of 5. So this one goes left and that one goes right. But why do they do that? Because they can both go north from the rules, right? Right. This one needs to check here, here, and here. So why would it go west unless it's going northwest? But if it's going northwest, why would this one go north? Oh, no. It doesn't tell us which one we're checking. F. Okay, so we start at the initial state. I need to print out each one we're checking at each iteration. So I need these. And this is before proposed moves. And then we print out the results. So we get, this is our first set of moves after the initial. We are checking for north, which is -1. This is our second set of moves. We are checking for south first, then east, then west, then west, then east. So this checks south, right? Which succeeds by the logic that we've done. I'm not iterating over the checks correctly, am I? Finally, at the end of the round, the first direction the elves considered is moved to the end of the list of directions. That's what we're doing. For example, during the second round, the elves would try proposing a move to the south first, then west, then east, then north. Yes, that's what we're doing. But if you do this for the output that you are giving me, so we do this, right? We check north first here. And then here we check south first. So it doesn't move because what? These can't move up. These can't move east and west. So why would this one not move south, right? If this wants to move south, it can try. If this wants to move south, it can't. So it checks west and it can. Same for this one. It checks south first, then west. Neither of those are valid, so it goes east. These check south first. Neither of them can go south. This one cannot go west. It can't go east, and it can't go north. Same thing for this one, right? These two can't move. So this one, which can go south, doesn't for some reason. Why doesn't it go south, right? End of round 1. This is sitting here. This is south. That's what we need to check for the second round, right? So this is our starting position for the second round. we check south, and we can move south, but we don't. Oh, we don't move south because all of these are empty. That's why. So we need to do the is all of them empty check first. So if local checks .clone.iter flat map v is going to be a vec, right? We don't need to .iter because we're already cloning an iterator. This is an ivec2 array of 3 of them. So we can do v.iter.map vec plus elf, right? Did I mess up the references here? Oh, probably one of them is going to be, all right, let's go find out. Cannot add an ivec2 to ivec2 3. That makes sense because I need to call it that. So we map over these, and then for all of them, we do the field.get. And we don't need to do these because we can do just, why is this inside of that? Okay, there we go. So now we can do this, right? So for the local checks, we clone the iterator, we flat map over the iterator, flattening everything into the position that the elf is going to be in. We take all of those values, which we can unique here for some minor performance games, I guess. For all of those unique values, field.get needs to be none. If all of them are none, then we continue. Not yet implemented on 148. I think that's fine. Round 2 then doesn't get this actually, because if let sum equals possible move, if this is true, then we don't do possible move. Proposed moves needs to get the elf. So we snag this, we put it here, do want this to be elf. So it's going to be that. And then we look at round 2 again, and we've got 1, 5 space. That looks correct. So it was really just our not checking for, check for all empty around elf, check for possible move in a direction. All right. We don't need to print the proposed moves anymore. We don't need to print the rounds anymore. Actually, yes, we do need to print the rounds because I'm going to check the 10th iteration of this, 0.10. So this is what it looks like. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 12 and 11. So that is the right number. If we look at it, it's 1, 1, 3, 1, 3. 1, 1, 3, 1, 3. That looks right to me. I'm going to call that correct without really checking everything. All I was doing there is 1, 1, 3, 1, 3, and I was holding in my head like the side of the board that they were on. Let's get rid of those print lines. Print field doesn't do anything anymore. And then here, not print, that's the wrong spot. Here then, right? We've got x2 and x1 already. So if we take these values and we multiply them together, we end up with the min box size. And then we can't just do btree.length. Well, actually we can. We can do a btree.length. That is right. So we do min box size minus field.length. And if we toString that as usize, if we toString that, then our test passes. Part 1 works. So because we're only storing the positions in our field, our hash set, that have an elf in them, when we get the minimum and the maximum bounding box for the X positions and the Y positions, that bounding box contains every elf that's on the field. So this is the maximum, this is all of the cells, the size of all of the cells. And then field.length, our hash set, is the size of all of the elves only. So if we subtract these two, then we get all of the empty spaces. Now, we do need to hope that this works for the input, as always. Let's do cargo run bin part 1. I left some logs in there, 3987 post. That's the right answer. We've got part 1. Part 2, it seems you're on the right track. Finish simulating the process and figure out where the elves need to go. How many rounds did you save them? In the example above, the first round where no elf moved was round 20. Figure out where the elves need to go. What is the number of the first round where no elf moves? Okay, I think we can figure that out. I think that's actually really easy for us. So instead of doing field equals here, we're going to let new field equal. Oh, actually, I'm going to wait because we're going to take all of this code and copy it into part 2 here. And I'm going to get rid of these check prints as well. So we've got process part 2. I think all of the logic still counts, but instead of doing field equals, we're going to do let new field equals proposed moves. And I think that we can do if field equals proposed moves, else field equals proposed move. So let's get the tests running because they will fail. Let's move the ignore up a bit. The first round where no elf moves is round 20 for part 2. And expected struct hash set found struct hash map. Oh, this is new field, not. So left is still 110 because we're not even breaking in this. This is the loop, right? Yep. So we're going to infinite eyes this loop. So for I and 0 dot dot, I is our round. I think that we are going to do for I and 1 dot dot so that we don't actually need to do a +1 later. And this is moves, whatever. Of course, this is the scaling problem that they were talking about where there's, I don't know, a more efficient way to do this or something. So the test is taking a really long time to run. If we compile it in release mode and run it while we take a look at the problem again, it seems weird that this would take that long. So I want to say that I am doing something wrong. Yeah, so this should hit 20 and stop is what I thought would happen. For I and 1 dot dot, right? It should hit 20 and stop. This is the moves. Oh, you know what I'm not doing though? We do need to break here because if we never break, guess what never happens? That's right. Rounds doesn't exist. So it's something that we need to create. We can create it anytime above this. So let mute rounds equals usize, I think, or not equals usize. Let rounds equals 0, which will make it be usize, which I think will be fine here. That probably says that it's never read. Value assigned to rounds is never read. Yep, that's totally fine. And then for the answer then, none of this math matters. So it's I.toString, right? Or rounds. Rounds is what we called this. Rounds.toString. So we've got 19 on the left and 20 on the right. I did it from 1. If I do it from 0, I get 18, right? I still get 19. Really? Why do I get 19 for both of them? Because it doesn't matter. Why are 1 and 0 the same is an interesting question. But this is fine. I think that this is just rounds plus 1.toString. I was trying to be cheap earlier by hoping that we could do the number in the loop, but that did not work. So if we cargo run bin part 2, since we already ran the release, we'll get some value out, 938, and it works. So we got both stars today. Dang, it's getting late for me. It started late and everything. Okay, let's go over the code quickly because this was a decently long recording. For part 2, the only change that we needed to make is if the hash set that we're building up here, the one that we're already collecting into and things like that, for the proposed moves is equal to the field that we already have, then this round is the round that we need to stop at. So we set rounds equal to I, we break out of the floor loop. Otherwise, we just keep doing what we did in part 1. And then we need to do rounds plus 1 for reasons unknown to me, because 0 and 1 for the loop do the same thing. Oh, you know what, actually? I'm also super lucky that I switched it back to 0 because we're skipping on I too. Oh, dang, that could have been bad. Okay, so overall, we've got this process whatever function. We've got this field that we parsed out. I've talked about parsers so much this month. I'm going to let you read or watch one of the other videos for that. I think we talk about iterators and that stuff in all of them. We set up the checks to be for north, south, west, and east. Our zeros are at the top, so going north is -1 for the y-axis. We use ivec2s to keep track of everything, make sure we're doing x's and y's. Then the interesting part here is that we take checks, right? This vec, we iterate over it, and we cycle that iterator. So we've got a continuous infinite loop of all 4 of these checks. We name that checks iterator. Inside of our loop, we need to take 4 of those values. In this case, I've chosen to clone checks iter, which is just the cycled iterator. And when we clone it, we skip I values, right? So for 0, we skip 0, and then we take 4 of them. So we take a collection of 4 of them. If we skip 1, this moves us forward 1. So instead of having 1, 2, 3, 4, we get 1, 2, 3, and then we cycle back around and we get 4. So this keeps giving us over and over the next set of 4 checks that we need to perform in the order that we need to perform them. We could definitely do this in a way that just kept iterating rather than cloning this. But cloning the iterator is pretty cheap for us anyway, so it doesn't really matter. Then we create a hash map from the desired moves that each of our elves wants to move to based on the rules to the list of elves that wants to move to that position. We use this later to find out how many elves want to move into a given position. For every elf, we check to see first if all of the spaces around it are empty. We do this by doing local checks. We could do this in a number of different ways, actually. For example, if we wanted to do a 0.3 Cartesian product with 0.3, then we could also get a 3x3 square that we would add the position of the elf to that we would also get. I chose to do it with local checks instead, but you could also do it some other way. It doesn't matter. If all the spaces around the elf are empty, we have to insert it. So we insert it into our proposed moves, and continues this for loop. It continues the next iteration of the for loop. If that's not true, then we check for a possible move from the order that we were given with checks. In this case, I think I've got some extraneous clones here. I'm not too worried about that though. I moved some code around, wrote some stuff, can always remove it. So we check in the order of each of the arrays of 3 for the checks that we need to do for north, south, west, and east. If any of them have all empty spaces, that means we can move in that direction. So we iterate over the vec of 3 checks. We check each position combined with the elf position. So we get like the -1 from the elf position for the y index. If they're all none, then sum, because this returns a Boolean, and then sum is a function on Booleans. Then we transition from a true into sum with the middle value of the checks plus the elf position. So this is either directly north, directly west, directly east, or directly south. That gets returned into possible moves. So we've got sum ivec2. It's really nice that we used ivec2s here because, or uvec2s or whatever, it would have been cool too, because we can directly do the addition here and we don't have to do any like tuple destructuring. If we've got a move that we need, or if we've got a move that the elf wants to move to, then we get, using the entry API out of our hash set, that particular move. We're also using our hash here because move is a keyword in Rust. So if I do that, it doesn't work. So we have to use our hash to be able to use the word move as a variable name. So we get the proposed moves using the entry key of an ivec2 from that move that we just found. If it's there, we modify it, push the current elf position into the vec, or if it's alone, we insert it with itself. If we don't have a possible move, then we just insert the elf at its current position. So the difference between these two is that the key is where we want to go, and the value is which elf is going to move there. So here's a potential new position, but here is a potential same position. Once we get all the proposed moves, we can iterate over them and use some logic to pull them into a hash set. We collect into this hash set of ivec2s. If there are multiple elves to move, that means that no elves can move. So we take the elf positions and we put them into the hash set. If there's only one elf that wants to go to a given position, we let it go to that position by just giving back the ivec2 of the new position. All that's collected in the hash set. For part 1, we use Itertools. So we take our hash set, iterate over it, map for v.x and v.y, and use the min-max function to get the minimum and the maximum for x, and then the minimum and maximum for y. We use let sum because if this doesn't succeed, we did something wrong in the advent of code example. So we destructure min-max, if let or if let else, etc. allow us to destructure variants of any arbitrary enum, not just sum or result or something like that. So we get the x1 and x2 values out of these tuples. We get the minimum box size by doing the bigger x value minus the smaller x value, plus 1 because we're 0 indexed, times the bigger y value minus the smaller y value, plus 1 because we're 0 indexed. That gives us basically x times y for the box size, which we need to subtract from the length of the field because the field hash set only has elves in it. So we have the number of elves that we have on the field right here, and we have the minimum bounding box around them on the left. For part 2, the only difference that we swap out is we don't do any of that math. And if the new positions, the new places we need to be, are exactly equal to the positions that all the elves just were in, then we set the rounds variable and we return that. So this was kind of a fun one. I hope you enjoyed the video. If you did, leave a comment, leave a like. Let me know how you did. And I'll see you for what I think is today's the 23rd, right? I think tomorrow is the last problem because I think 25 isn't a problem, but we'll find out. So I'll see you tomorrow. Have a great day.